Have you ever wondered, what exactly is time? It's a profound question, isn't it? Time, in its simplest form, is the continued sequence of existence and events, unfolding from the past, through the present, and stretching into the future. It's the invisible thread that weaves together the tapestry of reality. Time is also a key component in various measurements, a tool we use to sequence events, to compare the duration of different occurrences, and to quantify rates of change. Whether it's the ticking of a clock or the changing of seasons, we're constantly surrounded by the march of time. It's as omnipresent as the air we breathe, yet it remains one of the most elusive and enigmatic concepts. This ceaseless, invisible flow that governs everything from the smallest microbe to the vast cosmos. Time, often referred to as the fourth dimension, is an intriguing concept that has fascinated humans throughout history. Let's delve into the fascinating world of physics, where time takes on a whole new meaning. In the International System of Units, time is one of the 7 fundamental quantities. Here, the base unit of time is the second. But how do we define a second? It's not as simple as just glancing at your wristwatch. In physics, a second is defined by measuring the electronic transition frequency of cesium atoms. Quite a mouthful, isn't it? But this precise definition allows scientists to measure time with incredible accuracy. But time in physics is more than just a simple unit of measure. It's a key player in our understanding of the universe. Enter the concept of space-time and general relativity. General relativity, the brainchild of Albert Einstein, is our primary framework for understanding how space-time works. In this framework, time and space are interwoven into a single continuum. Now, here's where things get really interesting. According to general relativity, time can be distorted and dilated. It's not an unyielding, constant flow, as our everyday experience would suggest. Instead, time can stretch and squeeze, particularly at the edges of black holes. Imagine a cosmic ballet where time and space dance to the tune of gravity. That's the universe according to general relativity. But it's not just about black holes and the far reaches of the cosmos. These effects, albeit on a much smaller scale, are present in our day-to-day lives. Ever heard of time dilation? It's a real effect that comes straight from the equations of general relativity. It says that time moves slower the closer you are to a gravitational source. It's minuscule on Earth, but if you were to compare a clock at sea level to one on top of Mount Everest, the mountaintop clock would be ever so slightly ahead. In the realm of physics, time is not just a measure, but a vital part of our understanding of the universe. Time has not only been a subject of scientific study, but has also played a significant role in religion, philosophy, and navigation. As we journey down the annals of history, we see that time has been a constant companion, shaping civilizations and ideologies in its relentless march. Let's take a quick stroll through history. In ancient cultures, the concept of time was deeply intertwined with religion. The cyclical nature of time, reflected in the changing seasons and lunar cycles, was revered and often personified as deities. This reverence for time extended into philosophy. Greek philosophers, for instance, pondered on the nature of time. Plato viewed time as a reflection of the eternal, while Heraclitus believed that time was a manifestation of change. In the realm of science, the study of time has been a driving force for many breakthroughs. The need to accurately measure time led to the development of sundials and water clocks in ancient times, and later to the invention of mechanical clocks in the Middle Ages. These advancements in timekeeping played a pivotal role in navigation, enabling seafarers to chart their course across the uncharted seas with greater accuracy. Fast forward to the modern era, and we find that time has taken on additional layers of significance. Economically, time has become a currency. Time is money, as the saying goes. Every second counts in our fast-paced world, where efficiency and productivity are prized. On a personal level, the awareness of time's fleeting nature influences our behavior. It nudges us to value our moments, to live our lives to the fullest, conscious of the limited time we have. Time's influence extends beyond individual lives and permeates societal structures. It dictates our daily routines, governs our legal systems, and even shapes our cultural practices. Societies around the world have developed unique perspectives on time, some viewing it as linear, others as cyclical, reflecting their distinct cultural and philosophical outlooks. Thus, time isn't just a concept, but a crucial part of our daily lives and societal structures. It's a silent puppeteer, pulling the strings in the grand theater of life, shaping our past, present, and future. Defining time, however, is not as straightforward as it seems. The concept of time is inherent in our existence, yet its definition consistently eludes scholars. It's like trying to grasp water. The more you squeeze, the more it slips through your fingers. Despite this, various fields such as business, sports, science, and the arts have all incorporated some notion of time into their respective measuring systems. In the realm of physics, time is used to define other quantities, such as velocity. But here's the catch. If we define time in terms of such quantities, we end up in a circularity of definition. It's like saying, I'll tell you what an hour is if you tell me what a mile is, but then defining a mile as the distance traveled in an hour. It's a challenging conundrum, right? To sidestep this issue, physicists have come up with an operational definition for time. They say time is what a clock reads. It might seem overly simplistic, but this definition is immensely practical. It's like saying, I'll tell you what an hour is, it's 60 minutes, and a minute, that's 60 seconds. But then, what is a second? Here's where it gets interesting. A second is defined by observing a specific number of repetitions of a certain standard cyclical event. For instance, the transition frequency of cesium atoms. This definition allows us to measure time accurately, whether we're conducting advanced experiments or simply planning our daily routines. Periodic events and motions, from the apparent motion of the sun across the sky to the ticking of a clock, have long served as our standards for units of time. Despite its complex nature, we've found ways to measure and define time, aiding us in our understanding of the world. Yet, these definitions and measurements do not address the fundamental nature of time. They do not answer why time exists or why it moves in a single forward direction. But that's a mystery for another scene. So, how do we determine what time it is? We've been figuring out the answer to this question for millennia, using multiple systems to track the ceaseless march of time. Let's take a journey through the evolution of these systems. We start with the celestial. The apparent motion of the sun across the sky was one of the earliest ways we measured time. The rising and setting of the sun gave us the concept of a day, while the changing phases of the moon marked out months. Next, we looked closer to home. The free-swinging pendulum brought us into the realm of mechanical timekeeping. Each swing of the pendulum was a tick of the clock, a second passing by. But in our modern world, we've harnessed the power of technology to measure time with startling precision. Take the Global Positioning System, or GPS. It relies on a network of satellites, each with an atomic clock on board. These clocks send signals back to Earth, and by measuring the time it takes for these signals to reach us, GPS can pinpoint our location anywhere on the planet. Then there's Coordinated Universal Time, or UTC. This is the time standard used around the world. It's based on International Atomic Time, which itself is based on the vibrations of cesium atoms. But UTC also takes into account the slight irregularities in Earth's rotation, ensuring our clocks don't drift away from the true solar time. And let's not forget mean solar time, a system that averages out the variations in the apparent movement of the sun caused by Earth's elliptical orbit and tilted axis. This gives us a consistent measure of time, no matter the season. Now, these different systems might give slightly different results, but with careful measurements, we can synchronize them, bridging the gap between the atomic and the astronomical, the mechanical and the celestial. Through these systems, we've been able to create a standardized concept of time, essential to our modern society. And as we continue to explore the mysteries of the universe, who knows what new ways of measuring time we'll discover. Yet, the fundamental nature of time remains an enigma. This brings us to the intriguing concept of the space-time continuum, a realm where each event is assigned a unique set of 4 numbers, representing its time and position. This might sound straight out of a science fiction novel, but it's a cornerstone of modern physics. In this continuum, a simple event, like the explosion of a supernova or the collision of 2 particles, is defined by its coordinates in both time and space. But here's where things get really interesting. The observed time of an event can differ for various observers. Yes, you heard that right. Time, as it turns out, is relative. Depending on factors such as motion and gravity, your perception of time can be different from mine. In the grand scheme of the universe, time, as we understand it, is a fascinating and complex phenomenon, continuously challenging our understanding of reality.